What if the deepest view ever taken into space did not bring clarity, but confusion? When the James Webb Space Telescope looked farther into the universe than any instrument before it, scientists expected answers. Instead, it found ancient galaxies that seemed too old, massive structures that should not exist, and cosmic mysteries that may be forcing us to rethink everything we know about the origin of reality. If this kind of deep space mystery fascinates you, please take a moment to like, subscribe, and share the video. It truly helps the channel reach more curious minds. And thank you for being here. Your time, support, and curiosity mean more than words can say. Before we begin, feel free to leave a comment and let us know what time it is where you are and where in the world you're listening from. It is always amazing to see this journey through the cosmos bringing people together from so many different places. Now, settle in, relax, and let us begin the journey into what James Webb found when it looked too deep into space. Space looks calm from a distance. It presents itself as a clean black field scattered with cold points of light, each star fixed in silence, each galaxy suspended as if the universe has settled into a final arrangement. Yet James Webb enters that stillness and finds movement where certainty is supposed to live. Not the familiar movement of worlds orbiting suns or galaxies wheeling through the dark, but something deeper and more unsettling. The fabric of the universe itself appears to be stretching in a way that does not fully agree with its own past. For generations, cosmology rests on a simple confidence: the universe expands. Ever since the first evidence arrives in the early 20th century, astronomers learned to treat that expansion not as a vague impression, but as a measurable fact. Distant galaxies drift away. Light from ancient stars arrives reddened, stretched by the growth of space during its journey. From this, scientists begin to reconstruct a history. They estimate the age of the universe. They trace how matter gathers. They predict how everything might end. The expansion rate becomes one of the main numbers beneath the entire structure, a quiet constant supporting every larger conclusion. That confidence begins to weaken long before James Webb launches, but Webb turns the weakness into a wound. Two different methods of measuring the expansion of the universe keep returning two different answers. One method studies the nearby universe. It uses stars whose brightness varies in a regular pattern, celestial markers that allow distance to be measured step by careful step across nearby galaxies. The other method reaches much farther back, to the faint afterglow of the early universe, the ancient radiation left behind when the cosmos first becomes transparent. Both methods are grounded in decades of work. Both are refined again and again. Both are supposed to converge on the same reality. They do not. The disagreement is not dramatic in appearance. It is not the sort of discrepancy that seizes attention at first glance. It arrives as a gap of only a few units in the measured speed at which space expands across cosmic distances. In ordinary life, such a difference would seem trivial. In cosmology, it is intolerable. A small mismatch at this level spreads outward through every larger calculation. It changes the estimated age of the universe. It shifts the story of how galaxies assemble. It disturbs the balance between matter, and dark energy. What looks like a narrow technical problem begins to resemble a fault line running beneath the whole map of reality. James Webb is not built to solve philosophical problems. It is built to gather light, especially infrared light, the faint stretched glow from distant and ancient objects. Its mirror unfolds far from Earth, beyond the moon, at a place where heat and glare are kept to a minimum. There, with its sunshield spread wide and its instruments cooled to extreme stillness, it does what previous telescopes cannot do. It sees through dust. It sees deeper into time. It sees the distant universe not as a blur of weak signals, but as a field of precise measurable sources. And when it turns toward the stars used to anchor the nearby distance scale, it does not smooth over the old disagreement, it sharpens it. This is where the unease begins to change character. Before Webb, some astronomers can still hope that the tension comes from imperfect calibration, hidden dust, blending of starlight, or subtle flaws in the older data. The Hubble Space Telescope has already done the hard work of establishing the nearby scale, but Hubble operates close to the edge of what is needed. James Webb sees those same stars with greater clarity in infrared wavelengths, cutting through some of the confusion that visible light cannot escape. If the problem is caused by ordinary error, Webb should help dissolve it. Instead, Webb confirms that the contradiction remains. Across more than 1,000 pulsating stars in several galaxies, stretching out to roughly 130 million light-years, the pattern holds. The nearby universe suggests one expansion rate. The early universe suggests another. The discrepancy survives new instruments, new analysis, and new caution. It becomes harder to call it an accident. It becomes harder to dismiss it as noise. The measurements begin to look less like two imperfect estimates of the same truth and more like two accurate descriptions of a universe that refuses to be internally consistent. At first, the language around this problem stays restrained. Astronomers call it attention, a word that sounds technical and manageable. But the word hides the scale of the disturbance. Tension suggests strain inside a stable structure. What Webb reveals is close to a fracture. If the early universe and the nearby universe cannot be made to agree on how fast space expands, then something in the standard picture is missing. Perhaps dark energy, the mysterious influence believed to drive the acceleration of expansion, does not remain constant through time. Perhaps some unknown ingredient alters the behavior of matter or radiation in the early cosmos. Perhaps gravity itself changes subtly across vast scales. Each possibility sounds abstract. None is small. The difficulty is not merely that one number might be wrong. The deeper problem is that the universe seems to tell one story when viewed in youth and another when viewed in maturity. The afterglow of the early cosmos carries a memory of conditions shortly after the Big Bang. That memory, interpreted through the standard model of cosmology, predicts a certain present-day expansion rate. The nearby stars and galaxies, measured more directly, insist on a faster one. In effect, the universe appears to age into a different set of rules than the ones it begins with. It is as if a clock is built with perfect gears, only to discover that time itself starts running differently after the mechanism is set in motion. There are careful ways to frame this and more dangerous ones. The careful view says that cosmology has reached a threshold where precision exposes missing physics. That is plausible. Science often advances this way. Instruments become good enough to reveal a discrepancy, and the discrepancy leads to a refinement, a new particle, a revised constant, an overlooked interaction. The dangerous view is less comforting. It suggests that the modern picture of cosmic evolution, elegant and widely successful though it is, may rest on assumptions that only appear solid because the universe has never before been measured with this depth and this precision. Webb does not create the crack. It shines directly into it. What makes the moment especially strange is how quiet the evidence is. No star explodes to announce it. No galaxy tears itself apart in spectacular form. The anomaly hides in patient observation, in long exposures and carefully corrected brightness curves, in tiny shifts of light from stars that pulse across impossible distances. The crisis emerges not from chaos, but from order. The instruments behave. The numbers line up within each method. The data become cleaner, and the cleaner they become, the less the two pictures agree. That is when the question changes. It is no longer whether the universe expands. It is no longer whether the measurements are difficult. It becomes whether the cosmos has a hidden layer of behavior that all previous models smooth away. A universe with evolving dark energy would not be the serene broad structure once imagined. A universe with extra particles in its early radiation bath would be stranger than expected from its first moments. A universe in which gravity shifts its influence across scale or time would mean that the deepest law governing structure is not fixed in the way textbooks assume. Any one of these possibilities would reach into nearly every corner of cosmology. None has yet won. That uncertainty is part of the disturbance. The data point towards something missing, but the shape of the missing thing remains obscure. And so the first great shock delivered by James Webb is not a single object floating in darkness. It is a contradiction embedded in the background logic of the universe itself. Before Webb begins uncovering oversized galaxies, isolated black holes, or ancient structures that seem to mature too soon, it encounters a more fundamental unease. The stage on which all cosmic history unfolds may not behave as expected. Expansion is the broadest motion there is. It reaches between galaxies, across voids, through all of cosmic time. If that motion cannot be described by one consistent account, then every later mystery emerges inside a universe already slightly unmoored. The old picture does not collapse in a single moment. It remains powerful, predictive, and often astonishingly accurate. But something within it now flickers. The contradiction has been checked from multiple angles. Webb has looked where the earlier telescopes could not look clearly enough. The result is not reassurance. The result is a sharper version of the same impossible answer. The universe expands, but not with the clean simplicity once expected. Somewhere between its first light and its present age, something alters the rhythm. Whether that something is a hidden force, a changing property of empty space, an early ingredient now gone, or a deeper flaw in human models remains uncertain. What is certain is smaller and colder. James Webb looks into the distance for clarity and finds the first sign that the cosmos may not fully agree with itself. Once the expansion of the universe begins to look uncertain, distance and time both become less stable than they seem. The deep field images from James Webb carry that instability further. They do not simply reveal new detail in places that already fit expectation. They reveal objects that appear to arrive too early, too bright, too structured, too complete. This is where the unease leaves the level of abstract cosmology and takes visible form. A distant galaxy is not just a number in a model. It is a system of stars, gas, dust, gravity, and time. It has shape, it has mass, it has a history written into its light. And when Webb begins pulling that light out of regions once thought nearly empty, the history it reveals begins to conflict with the age of the universe itself. Astronomers expect the first few 100 million years after the Big Bang to be a rough and comparatively simple era. Matter has begun to gather, but not yet with the long patience needed to build enormous mature systems. The earliest galaxies in the standard picture should be small, irregular, unstable, and intensely active. They should look like beginnings. Their stars should be young. Their structures should still be assembling. Their growth should be constrained by the available time, because no matter how generous the physics becomes, time remains the first limit. Gravity can only work with what the clock allows. Webb looks into that era and finds something harder to place. In images near the constellation Ursa Major, in small patches of sky chosen for deep observation, it detects red sources that initially appear like faint distant smudges. At first there is caution. Deep field astronomy has always required it. Distance can make objects look older, redder, and stranger than they truly are. Dust can alter colour. Brightness can mislead. But as the light is analysed, a startling possibility emerges. Some of these early objects appear not to be tiny primitive systems at all, but massive galaxies already carrying stellar masses in the range of tens of billions of suns. In some interpretations, a few of them begin to approach the scale of the modern Milky Way, while existing when the universe is only a small fraction of its current age. That is the kind of result that immediately invites resistance. Not because resistance is emotional, but because the implication is severe. A galaxy cannot simply become massive because observers wish it to be strange. To accumulate such mass, it must either form stars at extraordinary rates, merge repeatedly with other systems in an impossibly compressed interval, or shine in a way that deceives astronomers about what it truly contains. Every route leads toward a problem. If the mass estimates are broadly correct, then the early universe is building large structures much faster than standard simulations allow. If the brightness comes from hidden black holes rather than starlight, then another mystery opens, because those black holes would themselves need to become massive far too soon. Even the least dramatic explanation leaves the timetable under strain. The sense of violation comes from how familiar the rules of galaxy formation seem before this point. In the standard account, dark matter forms the invisible scaffolding. Ordinary gas falls into those gravitational wells, cools, condenses, and begins forming stars. Small systems appear first. Larger ones arise through gradual mergers and steady inflow. The process is not random, but it is not instantaneous. It unfolds across hundreds of millions and then billions of years. Cosmic structure grows the way a forest grows, with scattered beginnings, uneven density, and long intervals of development. What Webb finds suggests moments when the forest appears fully standing almost as soon as the ground cools. Some of these systems become informally known as universe breakers, not because the term has formal status, but because it captures the mood surrounding them. They do not merely stretch the existing picture. They threaten to force a rewrite of the opening chapters of cosmic history. The name is dramatic, yet the underlying concern is precise. If the early universe can produce galaxies with such apparent maturity, then either star formation is vastly more efficient under primordial conditions than expected, or the light from these systems is being powered by mechanisms not yet fully separated from starlight, or the relation between visible light and actual mass is less reliable in the young universe than it seems. Each explanation carries consequences. The most straightforward version is also the most disruptive. Perhaps the first galaxies do not grow gently. Perhaps they form inside extremely dense reservoirs of gas that convert matter into stars with astonishing speed. In that case, the early universe is not a slow rehearsal before complexity begins. It is a brief violent era of overproduction. Regions of space collapse fast, ignite fast, and mature fast. The quiet hierarchy of gradual assembly gives way to something more abrupt. A cosmos that rushes into structure before existing theories predict it should. This has implications beyond the galaxies themselves. Dark matter would have to clump earlier or more strongly than current models suggest. The supply of cold gas would have to remain abundant under conditions that should also generate fierce radiation from newborn stars. Feedback effects, the tendency of intense star formation to heat and disrupt further collapse, would somehow fail to halt the process. In other words, nearly every balancing mechanism built into the standard picture would need to weaken just when it should be strongest. There is another path, and it is in some ways more unsettling because it shifts the mystery from galaxies to engines hidden inside them. If these luminous red objects are not truly dominated by stars, then much of their power may come from actively feeding black holes. Gas falling toward a black hole heats and glows, especially in the young dusty universe where light is easily reprocessed into infrared wavelengths. A compact energetic source can imitate the broad glow of a galaxy, particularly at extreme distance where only limited detail is available. This may reduce the required stellar mass, yet it does not restore comfort. It merely transfers the problem. A black hole powerful enough to dominate such a system in the early universe would already need surprising size and maturity. Instead of galaxies growing too quickly, black holes are doing so. The timeline remains broken. Follow-up spectroscopy begins to matter here because images alone can seduce. Webb is not only a camera, its instruments can separate light into its component colors and identify chemical signatures, motion, and distance with far greater confidence. Those follow-up observations do not remove the mystery. In some cases, they refine the distances and bring mass estimates down from their most extreme early versions. But even when the first shock softens, the core problem remains. Many early galaxies are still brighter, denser, and more evolved than expected. Their stars appear to have formed quickly. Their structures appear more established than they should be. Their presence forces cosmology into an uncomfortable middle ground where the strongest claims are trimmed. Yet the anomaly survives. That survival is what matters. It is easy to dismiss a first announcement if later work moderates the conclusion. It is harder to dismiss a moderated conclusion that remains troubling after correction. The early universe keeps producing objects that behave like they have been given more time than they actually possess. It begins to look less like a nursery and more like a place where maturity arrives in flashes. And because these galaxies are seen by looking back in time, each one becomes a challenge issued directly from the youth of the cosmos. They are not late-stage systems altered by unknown local conditions. They belong to the opening era itself. Their existence suggests that from the start, cosmic structure may have been capable of leaps rather than increments. There is also a subtle psychological shift in how these discoveries feel. The expansion tension is invisible until measurements are compared. These galaxies are visible anomalies. They sit in the images. They shine through the dark. The eye can rest on them even before the mind fully understands the numbers. Faint red points become physical symbols of a wider disorder. They are the first ancient cities where only campsites should exist. That simple visual fact gives the problem unusual force. A patch of sky that ought to contain only small beginnings now appears occupied by systems already carrying the weight of history. The effect ripples outward. If galaxies build faster, then stars enrich their surroundings faster. Heavy elements may appear sooner. Dust may form sooner. Planets may have the raw materials for assembly sooner. In the standard story, complexity emerges in stages, each one waiting for the products of the last. But if the early universe accelerates those stages, then complexity itself begins creeping toward the beginning. The cosmos may become chemically and structurally rich far earlier than believed. That does not mean life or intelligence appears early. It means the physical groundwork for unexpected richness may be laid almost immediately. Such possibilities remain speculative, but they grow from a concrete observation. The opening universe does not look as primitive as it should. The more careful astronomers become, the more they try to separate what is certain from what is inferred. Distances are measured, spectra are checked, alternative explanations are tested. Yet the pattern continues to provoke. One early galaxy can be an oddity. A population of them begins to resemble a new rule glimpsed beneath the old one. And once that possibility enters the frame, other Webb discoveries start to change meaning. Massive early galaxies no longer look like isolated surprises. They become part of a broader suggestion that the young universe is not merely younger than the present one. It may operate according to an intensity and efficiency that standard cosmology underestimates. The deep field then ceases to be a passive record of remote light. It becomes evidence of a cosmos that organizes itself with alarming speed. In that speed there is no need for fantasy. The known ingredients are enough to create unease: gravity, dark matter, gas, radiation, time. These are ordinary cosmological ingredients. What is extraordinary is the pace at which they appear to work together when Webb looks far enough back. A galaxy should carry the memory of how long it takes to become itself. These galaxies appear to carry the memory of a longer history than the universe around them can plausibly supply. That contradiction does not yet resolve into one explanation. It remains suspended between possibilities. Perhaps the masses are still overestimated in subtle ways. Perhaps starbursts in the early universe are more efficient than any modern analogy suggests. Perhaps early black holes masquerade as galaxies. Perhaps something about the first conditions of matter, still missing from the models, permits rapid assembly on scales not yet understood. None of these possibilities is trivial. Each one opens onto a different revision of the cosmic story. And so the second great disturbance in the Webb era takes form. The universe not only expands in a way that resists consistency, it also seems capable of building grand structures before enough time has passed to justify them. The contradiction moves from the background law of expansion into the visible architecture of space. The first galaxies are not supposed to look ancient, yet in Webb's field of view, some of them do. They appear as if they have crossed an impossible distance not through space, but through time itself, arriving already burdened with the mass and complexity of a later age. The question that follows is no longer whether the universe hides surprises. That is already clear. The question is whether its earliest darkness contains engines of growth far more powerful than anyone expected, and whether those engines are also responsible for the next class of objects Webb begins to uncover. Objects that seem to emerge not alongside young galaxies, but ahead of them, as if darkness itself is learning to organize before starlight has properly begun. The early galaxies already strain the timeline, but they still belong to a familiar category. However strange their speed of growth may be, they are still made of matter arranging itself into something recognizable. Stars gather, gas cools, light spreads through dust. A galaxy, even an impossible one, remains part of a known family. The next disturbance James Webb uncovers is harder to absorb because it seems to reach beneath that family and into a darker order of objects altogether. In several regions of the early universe, Webb begins to find signs that enormous black holes are present not at the end of a long sequence of cosmic development, but near the beginning, in places where the sequence itself should barely have started. This changes the mood of the mystery. A galaxy that forms too fast suggests that cosmic structure is more efficient than expected. A black hole that appears too early suggests that darkness may organize itself before starlight is ready to follow. For a long time, the broad story of black hole growth appears straightforward, at least in outline. Massive stars live quickly and die violently. When enough mass collapses inward, gravity overwhelms every opposing force and leaves behind an object so dense that escape becomes impossible once a certain boundary is crossed. These stellar remnants can then merge, feed, and grow in the centers of galaxies through repeated mergers and long accretion of gas. Some eventually become supermassive. The process is dramatic, but it still unfolds in steps. It depends on stars first existing, then dying, then leaving seeds that have time to feed. The young universe does not seem old enough for the largest versions of this process to have run their course. Yet Webb keeps finding indications that they already have. Some of the most troubling cases appear in the form of compact red sources, little points of infrared light that seem too bright for their apparent size. At first glance, they can be mistaken for early galaxies, or for galaxies whose masses are being exaggerated by distance and dust. But in some cases, the light looks too concentrated, too intense, too compact. It carries the fingerprint of matter falling inward at extreme speed, heating as it spirals toward a deep gravitational well. That pattern implies an active black hole, and not a modest one. These are not small stellar remnants hiding in corners. They appear to involve black holes with masses reaching into the millions of suns when the universe itself is only a few 100 million years old. That is the point where timing becomes almost unbearable. A supermassive black hole in the modern universe is not a surprise. The Milky Way has one. Most large galaxies appear to have one. But in the early universe, the clock is still running far too close to the beginning. To reach such masses by the conventional route, the first stars must have formed quickly, died quickly, left black hole seeds, and then those seeds must have fed at high efficiency almost without interruption. The mathematics of that growth are not impossible in the strictest sense, but they leave little room for delay, instability, or wasted time. Real cosmic environments are rarely so cooperative. Feedback from radiation should interfere. Gas supplies should fluctuate. Mergers should take time. Each difficulty narrows the path. Webb begins to make that narrow path look implausibly crowded. Among the objects drawing attention is a source informally discussed as a naked black hole, an enormous active black hole with surprisingly little galactic structure visible around it. That description may simplify a more complicated system, and astronomers remain careful with such language, but the deeper impression remains. In some cases, the black hole seems easier to see than its host. That is backwards. In the standard expectation, a black hole grows inside a galaxy, nested in a dense central environment, fed by the gas and stars surrounding it. Even when active, it is usually understood as part of a larger system. Yet these early sources sometimes appear as though the black hole has leapt ahead of the galaxy, reaching maturity before its home finishes forming around it. It is like finding the furnace before the house exists. That inversion matters because it suggests that black holes may not simply be passengers in the story of galaxy formation. They may be among its earliest and most forceful drivers. If a central black hole ignites quickly enough, its radiation and outflows can regulate the gas around it, alter star formation, and shape the entire later structure of the galaxy. In that case, the early universe is not building galaxies first and black holes afterward. It may be building both in a more entangled and violent sequence, with black holes sometimes taking the lead. The suspicion deepens when Webb data are combined with observations from other instruments, especially X-ray observatories that can detect the high-energy signatures of accreting black holes. Some distant objects light up in ways that ordinary star formation alone cannot easily explain. The signal does not merely indicate age or distance, it indicates appetite. Matter is being consumed. Energy is being released with a compact intensity that points toward a feeding black hole. The problem is not that such objects exist. The problem is how soon they exist and how large they already appear to be. That is where speculation begins pressing against the boundary of what the data permit. The most conservative response is to push the known process harder. Perhaps the first black hole seeds are much larger than once assumed. Instead of forming only from ordinary stellar collapse, some early stars may be extraordinarily massive, hundreds of times heavier than the Sun, leaving behind unusually large remnants. Under the extreme conditions of the young universe, with pristine gas and little heavy element cooling, such giant stars may be easier to form than in the present day. If that is true, then the first black holes begin life with a useful advantage. But even a large head start may not be enough. Many of Webb's early black hole candidates seem to require not just large seeds, but relentless feeding. The black holes would need to accrete matter near their theoretical maximum rate for long stretches, perhaps even above that rate during brief violent episodes. Such growth is not ruled out, but it is hard to sustain in detail. Radiation from the feeding process should push matter away. Surrounding gas should become turbulent and unstable. The universe would need to provide extraordinary efficiency in an era already expected to be chaotic. There is a second possibility, one that becomes increasingly difficult to ignore as Webb finds more early luminous compact objects. Perhaps some black holes do not descend from stars at all. Perhaps they form directly from the collapse of enormous gas clouds before stars have time to complicate the picture. In that scenario, the young universe contains regions so dense and so hot that ordinary fragmentation into stars is suppressed. Instead of breaking into smaller pieces, a huge cloud continues collapsing inward until it creates a black hole of great initial mass. This is known in general terms as direct collapse, and it has long been discussed as a possible route to early supermassive black holes. Webb does not prove the process in a single decisive observation, but its discoveries make the idea feel less like an exotic loophole and more like a serious contender. Direct collapse is unsettling because it shifts black hole formation into an earlier and more primal phase of cosmic history. It suggests that under the right conditions, darkness can condense almost immediately out of the raw materials of the newborn universe. There is no need to wait for generations of stars, no need for a long chain of stellar deaths. A large black hole can appear in one catastrophic event, seeded by gravity itself before luminous structure has properly matured. If such events are common enough, they could explain how early black holes race ahead of their host galaxies. The host would then be assembling around an already powerful central object rather than producing it slowly. Yet even this explanation does not settle the deeper unease, it only relocates it. If the universe allows direct collapse black holes, then the early cosmos is more violent and more permissive of extreme structure than standard gentle narratives imply. Regions of space must exist where the balance between cooling, fragmentation, radiation, and angular momentum tips in just the right way to create a massive gravitational sink almost at once. That is not impossible. It is simply a very different opening scene from the one many older models quietly assume. Then there is the most radical possibility, the one that moves from difficult astrophysics to the edge of cosmological speculation. Some black holes may be primordial. They may not form from stars or gas clouds at all. They may be relics of the first moments after the Big Bang, created when density fluctuations in the infant universe briefly become so extreme that certain regions collapse directly into black holes before atoms, stars, or galaxies exist. This idea has lived on the margins of cosmology for decades, sometimes invoked in discussions of dark matter, sometimes as a theoretical curiosity, often constrained by observations but never entirely erased. Webb does not confirm primordial black holes, but it changes the emotional balance around them. When black holes appear too early and too massive for ordinary histories, primordial origins stop sounding like pure fantasy and start sounding like one more possibility among several imperfect answers. A primordial black hole is a disturbing object not because it is monstrous in size, but because of what it represents. It would be older than every star, older than every galaxy, older than the chemical complexity that later fills space with planets, dust, and life. It would be a direct relic of the universe before the familiar universe begins. If such objects survive into later eras, they would function like buried seeds from a deeper creation story, hidden remnants of a time when the cosmos is not yet structured by the processes now considered normal. That thought makes the early black hole problem feel stranger than a simple timing issue. It suggests that the universe may carry fossils from its own first instant, still embedded inside the later architecture of galaxies. Webb adds to this feeling through the sheer number of candidates. One impossible black hole might remain an exception. A population of early active black holes begins to resemble a feature of the cosmos. The little red dots scattered through deep surveys become ambiguous in a revealing way. Some may be compact starbursts, some may be galaxies whose masses are initially overread, some may be accreting black holes. The category is uncertain, but the uncertainty itself is instructive. It means the early universe is crowded with luminous compact systems whose nature is not easily separated into modern boxes. The distinction between young galaxy and hungry black hole begins to blur. That blurring carries its own implication. Perhaps the first major light sources in the universe are not stars alone. Perhaps black holes contribute significantly to the rionization era, the long transition when ultraviolet light begins to strip electrons from neutral hydrogen across the cosmos. If so, then darkness is not only consuming matter, it is helping light the universe. The first significant beacons may be powered not by fusion in stellar cores, but by gravity in its most concentrated form. That would mark a subtle reversal in the emotional hierarchy of cosmic origins. The common image of the young universe places stars at center stage, gradually ending a long dark age. But Webb hints that black holes may be present almost from the first act, glowing through the infall of gas, influencing their surroundings before ordinary galaxies have fully declared themselves. In that case, the age of first light becomes less innocent than it sounds. It is not merely the moment when stars awaken. It may also be the moment when deep wells of gravity begin feeding in earnest. This is why the early black hole discoveries feel colder than the earlier galaxy anomalies. Galaxies forming too quickly still imply abundance. Black holes forming too early imply compression, collapse, and consumption. They suggest that the universe does not wait for complexity to emerge gradually. It may produce extreme gravitational objects almost immediately, then let later structure grow around them like frost forming around a buried nail. As Webb continues searching deeper into cosmic time, this possibility becomes harder to set aside. The first darkness may not be empty delay before illumination. It may be active, seeded, and already under tension. Something in the early universe appears ready to gather matter with terrifying speed. Whether that something is direct collapse, impossible feeding, primordial relics, or some mixture not yet understood remains unresolved. But the pattern is becoming hard to ignore. Before the first era of familiar galaxies has fully settled into view, Webb finds signs that immense gravitational engines are already there, waiting in the dark, feeding on the raw universe, as though the cosmos begins not only with light struggling to ignite, but with darkness already learning how to grow. Once the possibility of early black holes enters the story, the next question becomes unavoidable. If these objects really exist in such large numbers and at such early times, by what mechanism do they form and grow quickly enough to appear in Webb's field of view? It is one thing to admit that the clock seems too short. It is another to imagine what kind of universe can close that gap. This is where the narrative of orderly build-up begins to give way to something harsher. The early cosmos no longer looks like a patient workshop gradually assembling large structures from small beginnings. It begins to resemble a place of sudden collapses, brief violent feeding episodes, and unstable environments in which a black hole can gain enormous mass before its surrounding galaxy has time to settle into anything like maturity. In older accounts, growth is slow because it seems reasonable that it should be slow. Matter falls inward. Radiation pushes back. Angular momentum keeps gas from plunging directly to the center. Stars form, explode, stir their surroundings, and complicate any simple funneling of material into a compact object. A black hole, in this view, is not impossible to feed, but it is difficult to feed continuously and at high rates for long periods. The Eddington limit stands as a useful guide to that difficulty. It describes the balance point where outward radiation from hot infalling matter becomes strong enough to resist further inflow. In plain terms, A feeding black hole should eventually start blowing at least some of its own food away. This does not stop growth. It merely imposes discipline on it. Webb keeps uncovering signs that the early universe may often ignore that discipline. One of the most suggestive examples involves an active black hole known in recent research as a rapidly feeding source in the young universe, one that appears to be accreting matter at a rate many times above the standard theoretical limit. Such objects do not simply challenge detailed models. They challenge the intuitive picture of how a black hole should behave when it grows too hungry. A source like this seems to find a way around the normal pressure barrier, either by trapping radiation inside the inflow, by feeding through dense irregular streams, or by cycling through bursts so intense that the average growth rate far exceeds what earlier expectations treat as sustainable. Whatever the exact mechanism, the implication is disturbing. The young cosmos may permit episodes of black hole growth so extreme that a large fraction of a supermassive object's mass is gained in comparatively brief intervals. In that case, the problem of early black holes is no longer solved by steady patience. It is solved by violence compressed in time. This idea becomes more plausible because Webb's discoveries do not appear in isolation. Infrared data can reveal distant dusty sources hidden from visible light. But when those sources are paired with X-ray detections or radio signatures, a more complete image begins to form. Some early black holes are not merely present. They are active in ways that suggest the universe is feeding them under conditions quite unlike the quieter black hole growth seen in many nearby galaxies. Matter is not drifting inward decorously. It is surging, heating, and releasing energy under pressure. The process begins to look less like a lamp and more like a wound in a dense environment, bright because so much mass is trying to fall into so small a space at once. But rapid feeding alone may not explain the deepest tension. Even a black hole that grows at unusual speed still needs a seed large enough to benefit from that speed. This is why the concept of direct collapse becomes central. In this scenario, a massive gas cloud in the early universe avoids fragmenting into many stars. Instead, under rare but perhaps not vanishingly rare conditions, the cloud remains hot and stable enough against breakup that it collapses as a larger whole. The result is not a star cluster, but the birth of a black hole already far larger than the remnants of ordinary stellar death. Such a seed does not begin with a handicap. It begins with momentum. It begins close enough to supermassive status that later feeding can plausibly complete the job before Webb sees it. This route has a severe beauty to it because it strips away intermediate steps. It suggests that the universe can, in the right conditions, create an abyss almost in one motion. Gas gathers. Cooling is prevented or delayed. Fragmentation is suppressed. Collapse proceeds. There is no long family history of stars living and dying. There is only one failed star on a colossal scale, one region of matter that bypasses ordinary luminous life and falls directly into gravity's deepest architecture. The process has been explored in theory for years, often requiring exact environmental conditions such as strong ultraviolet backgrounds, low heavy element content, and particular dynamical flows. Those conditions may sound restrictive, yet the early universe, dense and chemically simple, may provide more opportunities for them than the modern one. Webb does not catch direct collapse happening in a single unmistakable sequence. Astronomy rarely offers such clean theatre. Instead, it reveals systems whose properties make direct collapse feel increasingly relevant. Among the most arresting is the object often described as the infinity galaxy, a colliding system whose appearance is strange even before its deeper significance becomes clear. Its figure resembles a luminous 8, two compact red nuclei with rings or arcs of light, as though two galactic hearts are suspended in a shared disturbance. Collision itself is not remarkable. Galaxies merge throughout cosmic history. But this case draws attention because radio and infrared observations indicate a powerful black hole in an unexpected place, not securely nested in one nucleus or the other, but in the turbulent region between them, surrounded by gas stripped and stretched by the collision, in a normal merger. The central black holes of the parent galaxies are expected to spiral together over time or remain associated with their respective cores until later stages. Here, the geometry seems different. The black hole appears suspended in a zone of active inflow between the colliding structures, where dense gas streams may have become unstable enough to collapse on their own. This makes the system feel like more than a merger. It feels like a laboratory in which the universe briefly reveals one of its hidden methods. If gas compressed between colliding galaxies can collapse directly into a massive black hole, then violent interactions are not only rearranging existing structures, they're creating entirely new gravitational centers in real time. That possibility matters far beyond this one system. It suggests that some of the early universe's giant black holes are not ancient survivors of a steady accumulation process. They are products of abrupt environmental crises. A collision funnels gas. The gas becomes dense and unstable. A direct collapse event occurs. A new black hole appears already massive enough to dominate its local region. The surrounding galaxy then evolves around an object born not at the end of development, but in the middle of catastrophe. Once this picture is allowed, the early universe changes texture again. It becomes not merely faster, but less hierarchical. The old sequence of seed, growth, merger, and maturity still exists, but it is joined by shortcuts. A violent universe loves shortcuts. It creates steep pressure gradients, dense streams, and conditions where ordinary bottlenecks can fail. The same young cosmos that forms oversized galaxies too soon may also produce black holes through routes too abrupt for the classical narrative. And if those routes are common enough, they help explain another recurring Webb surprise: the sheer frequency of large active black holes in eras where they should still be rare. There is a deeper implication here as well. Direct collapse and runaway feeding together suggest that supermassive black holes may not be the mature byproducts of galaxy formation. They may be among its most aggressive architects. A newly formed massive black hole begins affecting its surroundings immediately. Radiation from accretion heats nearby gas. Jets and winds can either suppress star formation or compress distant clouds into new bursts of it. The black hole becomes an organizing disturbance, a force that shapes the galaxy's later development. In that case, the relation between galaxy and black hole is not parent and child. It is more entangled, more unstable. Sometimes the galaxy may nurture the black hole. Sometimes the black hole may define the galaxy from a surprisingly early stage. This interpretation resonates with other Webb findings. Some early luminous compact sources appear too bright and too concentrated to be explained by stars alone. Some massive galaxies seem already quenched, as though the processes that build and halt star formation begin unusually early. Some colliding systems show central activity in places where existing models struggle to place it. None of these observations alone forces a revolution. Together they hint at a universe in which gravitational extremes emerge not reluctantly, but repeatedly, as though the first billion years are filled with episodes of sudden reorganization. That sense of repeated reorganization gives Section 4 its particular tension. Earlier mysteries concern timing. Here the mystery concerns temperament. What kind of cosmos behaves this way? A calm, expanding universe can still produce wonders, but Webb keeps revealing signs of a cosmos that spends its youth in convulsions. Dense gas rivers form between colliding systems. Invisible halos of dark matter channel matter into wells faster than expected. Black holes do not merely wait for their meals. In some environments they seem to be born inside the meal itself, condensing from the very structures that attempt to feed them. A black hole growing above the usual limit is already an affront to expectation. A black hole born directly from a catastrophic gas collapse is something stranger. It suggests that gravity at cosmic scale has modes of expression more abrupt than human intuition prefers. There is also a lingering unease in the observational challenge itself. The farther Webb looks, the more it relies on fragments of ancient light, stretched, reddened, and dimmed by cosmic time. The story is reconstructed from subtle clues: spectra, brightness profiles, surrounding morphology, companion emissions in X-ray or radio bands. This means every claim carries uncertainty. The universe does not deliver labels, it delivers signals. Yet uncertainty here does not diminish the mystery, it deepens it. Because even under cautious interpretation, the number of systems requiring unusual black hole growth remains too high to ignore. The edges of the evidence may blur, but the center holds. The young universe contains black holes too large, too active, or too oddly placed for older explanations to remain comfortable. And so the narrative of black hole origins broadens. There may be stellar seeds, but they are not enough on their own. There may be direct collapse, but perhaps only in privileged regions. There may be super Eddington bursts, but probably not in every case. The truth may involve several pathways operating at once, overlapping in time and environment. That plural possibility is itself revealing. It means the universe is not relying on one elegant route. It is using every available instability. Whenever matter can be channeled, compressed, heated, trapped, or deprived of ordinary fragmentation, gravity appears ready to exploit the opportunity. This is how the early cosmos begins to resemble a system of hidden emergency mechanisms, all designed to produce extreme mass in minimal time. Once that mood takes hold, the next discoveries begin to feel less like separate curiosities and more like symptoms of the same deeper character. The early universe is not merely young, it is opportunistic. It takes advantage of density, collision, asymmetry, and delay. It turns them into mass and radiance with alarming speed. In such a universe, enormous black holes no longer seem like impossible exceptions. They seem like the inevitable outcome of a phase of cosmic history more violent than the later universe remembers. Webb does not yet show the full machinery. It catches glimpses. A rapidly feeding source here, a collision with a misplaced black hole there, a compact luminous dot too old, too bright, too concentrated. Each clue on its own can be hedged. Together they sketch a hidden era in which matter falls through shortcuts toward gravitational extremity. If that sketch is even partly right, then the first billion years of cosmic history are not a slow dawn. They are a field of collapses, a time when entire systems can change identity almost instantly, when gas streams become event horizons, and when the universe discovers, very early, how to manufacture its deepest wells. After the violent architecture of early galaxies and black holes, the eye expects some relief in smaller things. A planet seems almost modest by comparison. It is a body of gas or rock or ice, a local event rather than a cosmic engine, a fragment of matter shaped by the gravity of a nearby star. Planets feel intimate because they belong to the same category as Earth. They orbit, they cool, they gather atmospheres if conditions allow. They seem less likely to overturn the grand narrative of the universe. James Webb does not allow that comfort to last. When it turns part of its attention toward planetary objects that drift free of starlight, it reveals a different kind of disturbance, one that does not depend on colossal mass or vast cosmic timescales. It reveals that even abandoned worlds can behave in ways that strain familiar ideas about how planetary systems form, how they survive, and what they're capable of doing once they're cast loose into the dark. In the Orion Nebula, a region already known as a cradle of young stars, Webb identifies a remarkable population of free-floating planetary mass objects. These are not worlds circling suns at measured distances. They move through space without a central star, isolated from the ordinary source of light and heat that gives a planetary system its structure. Such rogue planets are not entirely unexpected in theory. Gravitational chaos during the youth of a solar system can eject smaller bodies. Close encounters between giant planets can fling one outward. Interactions inside dense star-forming regions can strip a world away from its original home. A galaxy as crowded and dynamic as the Milky Way should contain such exiles. What shocks astronomers is not simply that Webb finds them. It is how many it finds, how young they appear, and how often they seem to travel in pairs. These paired objects become known as Jupiter mass binary objects, a cumbersome phrase that conceals how strange they are. Each component is roughly planetary in mass, yet instead of orbiting a star together with a broader family of worlds, the two bodies orbit each other alone. They drift through the nebula like a miniature system severed from any sun. Some are separated by tens of astronomical units, others by hundreds. Their very existence is awkward for standard formation models. Planets are expected to emerge inside disks of gas and dust around stars. Binary planets without a star are difficult to assemble in that setting, and difficult to keep intact during the same violent interactions that would be needed to eject them into interstellar space. A world might be thrown out. A pair of worlds, still bound together, is harder to explain. The more of these pairs Webb finds, the less they look like freak accidents. They begin to suggest that the early stages of planetary formation may permit outcomes that older models treat as marginal. One possibility is that some of these objects never really behave like planets at all during formation. They may arise more like failed stars or miniature brown dwarfs, forming directly through collapse inside turbulent gas clouds rather than inside a planetary disk. That would allow them to emerge already paired, the way binary stars do, only at much lower masses. But this explanation also carries a quiet shock, because it means the line between planet and star formation is more porous than comfortable categories imply. Objects with planetary masses may be born by stellar mechanisms. Worlds may come into existence not only as secondary features of suns, but as direct products of collapsing nebular structure. Another possibility remains more tragic. The paired rogue worlds may have formed in ordinary planetary systems and then been expelled together during phases of severe dynamical instability. In that case, the nebula is full of evidence that young systems are more chaotic than once imagined. It is not merely that planets wander. Entire subsystems are torn out and abandoned. The night between stars becomes crowded with survivors of gravitational disasters. In either interpretation, the emotional texture of the cosmos changes. Empty space is no longer empty between stars. It is inhabited by worlds that have slipped the discipline of stellar order. Webb's infrared sensitivity matters here because these objects are faint and cold. They do not shine by reflected starlight in any useful sense, because many of them have no nearby star to reflect. Instead, they glow with leftover heat from formation, a dim internal warmth that slowly fades as they age. To visible light telescopes, they would often be nearly invisible. To Webb, especially in star-forming regions where youth preserves some thermal glow, they emerge from the dark as a hidden population. The result is unsettling for a simple reason. The familiar solar system encourages the belief that planets belong to stars. Webb reveals a universe where many do not, or no longer do, and where some may never have done so in the first place. Their isolation would already be enough to provoke wonder, but the paired worlds of Orion are stranger still because they do not merely drift, they interact. They circle one another in broad, quiet orbits while moving together through the larger darkness of the nebula. A single rogue planet is an exile. A binary rogue planet is almost a remnant of companionship preserved after expulsion. A private gravitational bond surviving the loss of the central star that should have anchored both bodies. That private bond becomes even more intriguing when radio observations of some free-floating planetary mass objects hint at emissions that are difficult to place within ordinary planetary behavior. The sample script imagines signals from these worlds with a dramatic edge, and the reality is subtler, but not without its own mystery. Radio studies of substellar and planetary mass objects, including isolated bodies and brown dwarf-like worlds, reveal that some of them can generate powerful auroral activity and magnetic emissions far stronger or stranger than older expectations once suggested. When a planet or substellar object has a strong magnetic field, charged particles can be accelerated along that field and produce radio bursts. In the solar system, Jupiter offers a familiar version of this process, with radio emission tied to magnetism and interaction with its moon Io. But in isolated worlds without clear external companions or stellar wind environments, the source of such activity becomes more elusive. If rogue planetary bodies can generate intense magnetically driven emissions on their own, or through interaction with a close binary partner, then these worlds are not merely cooling inert balls of gas, they are electrically active systems. Their isolation does not make them simple, it may, in some cases, make them stranger. For the paired rogue worlds, the binary arrangement creates opportunities for tidal stress, magnetic coupling, and internal heating. Two bodies circling one another over immense spans can raise tides in each other, not unlike the way Jupiter's gravity needs Io and drives volcanic activity. Scaled into different masses and different magnetic environments, such coupling could keep interiors warmer, alter atmospheres, or power auroral processes long after any primordial heat should begin to fade. This is where the known observation opens into careful speculation. The concrete fact is that isolated substellar objects can be magnetically and atmospherically active in ways that are still being mapped. The widening possibility is that a rogue binary may become a self-contained weather and electromagnetic system, drawing energy not from a star but from rotation, tidal interaction, and internal dynamics. Such a world pair would not be dead in the usual sense. It would be dark, but busy. It would carry weather, storms, and perhaps even chemistry that owe nothing to sunlight. The wider implication is easy to miss because planets are so much smaller than galaxies, yet the scale of the revision is substantial. If a single nebula contains hundreds of free-floating planetary mass objects, many of them paired, then the Milky Way may hold vast numbers of orphan worlds. Some may be ejected giants still radiating the memory of lost formation heat. Some may be direct collapses from cloud fragmentation, born alone and never attached to a star. Some may host thick atmospheres, magnetic fields, or long-lived interior warmth. The galaxy between stars may be full of planetary environments that receive almost no light and yet remain physically active for millions or billions of years. That possibility presses quietly against one of the oldest habits of thought in planetary science. Heat, weather, and complexity are usually imagined as gifts of a nearby star. Webb hints that for some worlds, isolation does not end complexity. It changes the source. Internal heat from contraction, radioactive decay, or tidal distortion may sustain atmospheres and dynamics in profound darkness. A rogue planet may not be habitable in any ordinary sense, and the narrative need not drift into fantasy to feel the force of the idea. The deeper point is simpler. The classical map of where interesting planetary behavior should occur is too narrow. Strange weather may happen far from stars. Atmospheric layers may survive without sunlight. Magnetic storms may rage in solitude. The universe does not reserve complexity for illuminated places. There is also something psychologically disquieting in the way these worlds are found. They do not announce themselves with obvious brilliance. They are discovered because a telescope built to study the earliest galaxies can also perceive faint heat signatures in a nearby stellar nursery. In other words, the same instrument that exposes the first cosmic structures also uncovers hidden populations of wandering worlds much closer to home. The contrast is almost unnerving. At one scale, Webb reveals galaxies too old for their age. At another, it reveals planetary objects too detached for their category. The disorder is not confined to one level of cosmic structure. It appears everywhere the telescope looks carefully enough. The rogue worlds of Orion also force a new reading of planetary system formation itself. If ejection is common, then early planetary systems may be far more unstable than stable ones like the mature solar system suggest. Giant worlds may not settle quietly into final orbits. They may scatter, exchange momentum, disrupt one another, and cast some members into the interstellar night. In that case, every neat planetary system that survives may represent not the default outcome of formation, but the lucky remainder after a phase of hidden violence. A calm star with orderly planets may be the visible aftermath of earlier expulsions now forgotten. The galaxy would then be full not only of stars and their present families, but of planetary ghosts from families broken apart. And if some rogue pairs form directly from cloud collapse, an even stranger possibility emerges. Planetary mass objects may populate a shadow category of cosmic bodies, neither fully planetary in origin nor stellar in function, formed in the same nurseries as stars but too light to ignite. They would drift as solitary products of fragmentation, a parallel population born from the same dark clouds that produce stellar systems. The sky, under this view, is not merely filled with stars and the planets that attend them. It is filled with unattached worlds that owe their existence to multiple formation channels, some graceful, some violent, some still uncertain. By now, the pattern in Webb's discoveries begins to feel consistent even when the subjects change, large or small, early or nearby. The universe keeps revealing hidden abundance in places where expectation predicts scarcity or simplicity. Massive galaxies appear too soon. Black holes seem to outpace their hosts. Now rogue planets multiply in the dark and bind themselves into pairs where formation theory hesitates. The same underlying lesson returns in altered form. The cosmos does not use its available possibilities conservatively. It explores them fully, sometimes excessively, often in ways that the neatest models smooth away. A world without a star should be dim, cold, and mostly irrelevant. Webb turns that assumption inside out. It shows that a starless world may still have a history, a companion, an atmosphere, perhaps even a magnetic life of its own. It may move through darkness not as a dead stone, but as a small self-contained system with weather and internal drama that no daylight ever reveals. And if that is true, then the next planetary surprises do not need to come from isolation alone. They may come from worlds still close to stars, but assembled from the wrong materials, carrying the wrong chemistry, or clinging to atmospheres that should already have burned away. After all, once the galaxy admits that planets can survive without suns, it becomes easier to believe that planets with suns may also live by rules that no one expected. Planetary science depends on a set of quiet expectations, not rigid laws, but patterns repeated often enough that they begin to feel foundational. Rocky worlds are expected to emerge in the warm inner regions of disks rich in silicates, metals, and, crucially, reservoirs of water that can survive long enough in colder zones to be delivered inward later. Giant planets are expected to form farther out, where ices accumulate more easily. Atmospheres on intensely irradiated worlds are expected to erode under brutal stellar bombardment. The chemistry of young planetary systems is expected to follow recognizable gradients, because heat, pressure, and radiation sort material in ways that models have spent decades trying to refine. James Webb steps into this orderly picture and begins to find birthplaces and finished worlds that do not obey the expected chemistry, the expected resilience, or the expected balance between surface and sky. It is not merely that these planets are unusual. It is that the processes creating them appear to proceed with ingredients that seem wrong for the job. One of the clearest examples comes from Webb's studies of planet-forming disks, the flattened swirls of gas and dust around young stars where future worlds are assembled grain by grain, collision by collision, orbit by orbit. These disks are not decorative halos, they are factories. Their chemistry matters because every later landscape, atmosphere, ocean, and crust begins in those early mixtures. When astronomers study such disks, they expect to see familiar molecular signatures depending on temperature and location: water, carbon-bearing molecules, silicate dust, traces of organics, all arranged by the star's heat and by the disk's own internal structure. Webb's infrared spectrographs are unusually powerful here because molecules leave distinctive marks in infrared light. A disk does not need to be directly visible as a finished world. Its chemistry can be read in the glow and absorption of its gases and dust. In one young system inside a star-forming region, Webb identifies an inner disk that appears unexpectedly rich in carbon dioxide, while showing remarkably little water. The specific details of individual systems continue to be refined as observations accumulate, and astronomers remain cautious about how representative any one disk may be. But the larger impression is difficult to dismiss. In regions where rocky planets should be taking shape from hot mineral grains and water-related chemistry, Webb begins to see evidence that some disks may be chemically skewed in ways older assumptions do not naturally anticipate. The inner disk is not merely dry in a casual sense. It appears organized around a different balance of volatiles, with carbon dioxide far more prominent than the simple planet formation story would prefer. That matters because water has long occupied a privileged position in how scientists think about the assembly of terrestrial worlds. It shapes minerals, influences oxidation, affects the transport of material, and later becomes central to atmosphere and surface evolution. To find a region where the chemistry seems shifted away from that pattern is to realize that some rocky planets may begin life under profoundly unfamiliar conditions. The known possibilities for explaining such a disk are already strange enough. Intense ultraviolet radiation from the central star, or from nearby massive stars in the same stellar nursery, may break apart water molecules and drive hydrogen away while leaving oxygen behind to bind with carbon. In this picture, the disk is not born dry, it is chemically stripped. Radiation turns a potentially ordinary nursery into a harsher one, altering the inventory from which future worlds will be built. Another possibility is that the dust itself develops under unusual surface chemistry, with carbon dioxide ice or other carbon-rich coatings becoming more important than water ice in certain zones because of local temperatures, pressures, or the timing of grain migration through the disk. Either way, the message is the same. Planet formation is not occurring inside one universal recipe. It is taking place inside environments that can be chemically sculpted into forms with no close analogue in the solar system. The quiet shock of this realization grows when it is followed to its conclusion. A rocky world assembled in such a disk would not merely be Earth with less water. It might become a fundamentally different type of planet from the beginning. Its minerals would equilibrate under different conditions. Its atmosphere, if it forms, could inherit different ratios of carbon compounds to water vapor. Its crust and mantle chemistry might diverge long before tectonics or volcanism have time to shape them further. Even the possibility of later habitability would be altered at the root, because the world would begin with a different elemental mood. In earlier decades, exoplanet science often imagined strange planets as outcomes of familiar processes pushed to extremes. Webb suggests something harder to simplify. Some planets may be strange because their very starting materials are rearranged before the planet itself exists. That idea becomes more intense when the telescope turns from planetary nurseries to finished worlds living under impossible heat. Among the most discussed of these is the lava world orbiting the star known as 55 Cancri. It circles so close to its star that a year there lasts less than a terrestrial day. The planet is thought to be tidally locked, with one hemisphere facing perpetual irradiation while the other remains in lasting darkness. Temperatures on the day side rise high enough to melt rock and perhaps vaporize silicate material. For years, this world serves as a symbol of planetary extremity, a place so hot and so battered that it seems unlikely to preserve a substantial atmosphere at all. Many models treat it as nearly bare, or at most as a world with only transient vapors rising from a molten surface. Webb complicates that picture. By measuring thermal emission and the distribution of heat across the planet, it finds evidence consistent with some form of atmosphere or heat transport mechanism that prevents the day side and night side from diverging quite as severely as a completely airless world should. The exact composition remains debated, and careful interpretation is needed because observations of such extreme planets are difficult. Yet the broad implication remains startling. A world that should have lost any ordinary atmosphere long ago may still retain, rebuild, or continuously generate a gaseous envelope under conditions that appear hostile to atmospheric survival itself. Some interpretations point toward carbon monoxide or carbon dioxide-rich gases. Others consider mineral vapor or products of intense volcanism. The key disturbance is not tied to one molecule. It lies in the persistence of atmosphere where atmosphere seems least likely to survive. The traditional expectation is simple enough. A planet this close to its star should endure fierce stellar radiation and wind. Any primordial atmosphere left from formation ought to be stripped away quickly on geological timescales. If gases remain, then they're probably not ancient leftovers. They must be replenished. That means the planet's interior is no passive reservoir. It is actively feeding the sky. Volcanic outgassing, magma ocean evaporation, rock vapor release, and interior circulation become part of atmospheric maintenance. In this picture, the surface and atmosphere are not separate layers. They are one ongoing exchange, a feedback loop running under such extreme heat that solid crust may barely persist on the day side at all. The world becomes less like a planet with weather and more like a furnace whose vapors repeatedly condense, flow, and re-enter the cycle. This is where scientific fact begins opening onto a more speculative but still anchored possibility. On a world so hot that rocks soften and metals may vaporize, weather no longer means clouds of water or rain of methane. It means mineral atmosphere, molten transport, and possibly precipitation made not of liquid familiar to Earth, but of condensed rock species. Winds could redistribute heat and material from the bright side toward the dark side. Chemical compounds stable in one hemisphere could break apart in the other. Entire layers of atmosphere might be temporary, surviving only because the interior continually replaces what the star destroys. In such a regime, an atmosphere is not a leftover shell. It is an active geological exhaust system wrapped around the whole planet. The importance of this goes beyond one famous hell world. It suggests that planetary atmospheres are more resilient and more inventive than earlier frameworks allow. Worlds once written off as airless cinders may instead support dynamic envelopes sustained by internal processes. That does not make them hospitable. It makes them harder to classify. A close-in rocky exoplanet may not fit neatly into the category of bare rock or conventional atmosphere-bearing world. It may occupy an unstable middle state, constantly rebuilding a sky from its own dissolving body. In the sample script, this becomes an image of a world where rock rises into air and returns as mineral rain. The reality is more constrained, but the core mystery remains. Under enough heat, planet and atmosphere begin to exchange material so rapidly that the distinction between surface and sky starts to blur. Webb's broader contribution is to make such ideas feel less like speculative art and more like consequences of observed thermal patterns and chemical signatures. The telescope is not merely cataloguing exotic worlds. It is revising the range of conditions under which atmospheres can exist, the kinds of molecules they can contain, and the ways interior geology can sustain them. A planet does not need to resemble Earth to possess complexity. It may be locked, scorched, and nearly molten, yet still host an active envelope of gas and circulation. That realization adds a new layer of instability to the planetary story. Earlier sections of the narrative show galaxies forming too quickly and black holes growing too early. Here the surprise is subtler. Planets built from the wrong ingredients and planets living under impossible heat still manage to become chemically active systems. Disorder does not erase structure. It creates a more alien kind of structure. The same principle extends into other strange atmospheres Webb has begun to examine, including objects on the border between giant planets and brown dwarfs, where clouds may be composed not of water droplets, but of silicates, iron, and other condensates unfamiliar to everyday weather. In some isolated worlds, infrared observations reveal patchy cloud decks, shifting hot regions, and atmospheric variability far more complex than once assumed. Although some of those objects fall outside the classical planetary category, they are part of the same lesson. Atmospheric behavior is not reserved for temperate worlds under gentle sunlight. It emerges across a far wider territory of temperatures, pressures, and chemistries than the solar system alone ever suggested. That widening of territory matters because it forces a redefinition of what a planet is allowed to be. For a long time, exoplanet science operates by analogy. Hot Jupiter, super-Earth, mini-Neptune, ocean world, desert world. The names are useful, but they carry a hidden assumption that unfamiliar worlds can still be mapped onto a familiar base. Webb weakens that assumption. Some worlds may not be extreme versions of known classes. They may belong to classes the solar system never demonstrates. A carbon-shifted rocky planet assembled in a water-poor disk. A lava world maintaining an atmosphere through constant geological replenishment. A dark, isolated body with mineral clouds and auroral heating. These are not merely variants. They suggest that planetary physics explores a wider design space than human expectations originally permit. This becomes even more unsettling when placed beside the earlier discovery of rogue worlds. A planet can be ripped from its star and still remain active. A planet can form in a chemically distorted disk and emerge fundamentally unlike terrestrial expectations. A planet can orbit within catastrophic proximity to its star and still preserve some atmospheric complexity. The old assumption that stable starlight and moderate chemistry are prerequisites for interesting planetary behavior begins to dissolve. Webb does not make the universe more chaotic in the sense of randomness. It makes it more permissive. More things are allowed. More combinations remain viable. More edge cases become real objects. There is a hidden consequence here for how life-related speculation is usually handled, even though the script wisely avoids turning every planetary anomaly into an argument about biology. The important point is not that these worlds are habitable. Most are almost certainly hostile. The important point is that habitability itself rests on a deeper scaffolding of planetary diversity than older models recognize. A universe capable of producing dry carbon-rich rocky planets, mineral atmosphere lava worlds, and active rogue bodies is a universe in which the inventory of planetary starting points is much larger than once believed. That means every later discussion about which worlds might eventually become temperate, stable, or chemically rich enough for complexity must begin from a broader and stranger foundation. By now the pattern becomes unmistakable. Webb keeps discovering that nature is willing to build systems from ingredients that seem mismatched to the outcome. The disk lacks the chemistry expected for ordinary rocky worlds. The molten planet retains an atmosphere that should have vanished. The isolated substellar body grows clouds of metal, rich condensates in darkness. Each case repeats the same progression. A model predicts a boundary. Webb finds an object living just beyond it. Not impossibly beyond it, but far enough that the boundary itself needs revision. The effect is cumulative. The planet story grows less about identifying analogues to Earth and more about confronting the sheer adaptability of matter under unfamiliar conditions. That adaptability carries the narrative toward its next phase. If planets and disks can diverge this sharply from expectation, then so can the chemistry of the early universe itself. The same telescope revealing wrong worlds in nearby systems is also looking back into an age when the first heavy elements, the first dust, and the first complex structures should barely exist. And there too it begins to find signs of premature maturity, as though the cosmos is not only willing to invent unfamiliar planets, but willing to reach chemical complexity long before the timetable should allow. The wrong worlds around young stars are not an isolated curiosity. They are part of a larger pattern in which matter seems determined to become more complicated, more quickly, and in more varied ways than the standard narrative ever fully expects. The discovery of unfamiliar worlds is unsettling because it shows that planetary diversity outruns the categories built from one solar system. But beneath that planetary strangeness lies a deeper and older question. Before a world can be dry, carbon-rich, metal-clouded, or wrapped in a heat-borne atmosphere, the universe must first create the raw materials for such worlds to exist: carbon, oxygen, silicon, iron, dust grains, complex molecules, frozen compounds. All of these belong to a long chain of cosmic enrichment. In the oldest and simplest account, the chain begins with hydrogen and helium, the light elements forged in the first minutes after the Big Bang. Everything heavier must come later, inside stars and in the explosions that end them. Complexity, under that view, arrives slowly. First stars ignite in pristine gas. They live briefly, die violently, and seed their surroundings with heavier elements. New stars form from that enriched debris. Dust begins to gather. Planets eventually condense. The timeline is not arbitrary. It is meant to protect causality. Nothing chemically rich can appear before the universe has had enough time to make richness possible. James Webb keeps returning to that old sequence and quietly shortening it. One sign of this shortening appears in the study of very young galaxies that already seem too chemically mature for their age. In the early universe, galaxies should bear the marks of youth in more than structure alone. They should also be poor in heavy elements. Their gas should be closer to primordial simplicity, not because stars have never formed within them, but because not enough generations of stars should have lived and died to enrich the environment deeply. Webb does not always see that expected simplicity. In some distant systems, spectroscopic observations begin to suggest the presence of oxygen, carbon, nitrogen, and other heavy elements at levels that imply a faster pace of stellar processing than models comfortably predict. The galaxies are young in cosmic age, yet their chemistry already hints at repeated cycles of stellar birth and death. That is a difficult thing to explain if the opening universe is meant to be chemically primitive for any significant length of time. The issue here is not only whether heavy elements are present, it is how much, how soon, and in what combinations. A single burst of massive star formation can enrich surrounding gas quickly to a point. Very massive stars live fast. They burn through their fuel in only a few million years and then explode, releasing fresh elements into their surroundings. If the first generations of stars are unusually massive, unusually efficient, or unusually numerous, the early universe can become enriched faster than older average models once assumed. That is the conservative path toward explanation. It says the first stars are more extreme, not that the laws of nature are different. Yet even that path carries consequences. If the first stars are indeed colossal and short, lived in great numbers, then the universe enters chemical adulthood far sooner than expected. Dust forms earlier. Cooling becomes easier in later gas clouds. Star formation changes character. Planet-building materials begin accumulating when cosmic history is still very young. Complexity ceases to be the late reward of patience. It becomes one of the earliest habits of the cosmos. Webb's ability to read this early chemistry matters because ancient light arrives stretched into the infrared, where its instruments are most sensitive. Emission lines from ionized gas reveal what elements are present and how energetic the surrounding radiation must be. The patterns are subtle, and astronomers are careful not to overstate single detections. But the broader picture that emerges from multiple early systems is troubling in its consistency. The universe keeps showing signs of being ahead of schedule. Galaxies are too massive. Black holes are too mature. Now the gas between young stars already seems too enriched. The same story repeats at a different level. The cosmos does not merely build structures early, it also appears to process matter early, transforming pristine simplicity into chemically useful complexity with alarming speed. This change in the timeline has a physical consequence that goes beyond chemistry itself. Heavy elements cool gas more efficiently than hydrogen and helium alone. They allow collapsing clouds to fragment differently, to form different stellar populations, to create dust that blocks and re-radiates light, to alter the texture of entire galaxies. Once enrichment begins, the character of cosmic evolution changes with it. A universe enriched too soon is not simply a richer universe. It is a universe whose later development is reshaped from the beginning. Every subsequent generation of structure inherits those early changes. In that sense, the question of premature chemistry is not a small correction to early star formation. It is a revision to the opening conditions of complexity itself. The strange population known as the little red dots deepens this revision. These compact crimson sources, scattered through Webb's deep surveys, remain among the most ambiguous and suggestive discoveries of the telescope's first years. They are tiny in appearance, extremely distant, and often remarkably luminous for their size. Some seem point-like, as though powered by compact engines rather than extended star-forming regions. Others appear to have some broader galactic structure. Their redness can be explained partly by cosmic distance, because the light has travelled so far that expansion stretches it into the infrared. But distance alone does not resolve what they are. If they are galaxies, then many of them are unexpectedly dense, unexpectedly bright, or unexpectedly mature. If they are black hole-dominated systems, then the early universe again contains massive active engines sooner than expected. Either interpretation is difficult. The ambiguity does not weaken the mystery, it sharpens it. There is a reason these objects feel more disturbing than ordinary classification problems. A telescope is expected to discover new members of old families, another galaxy type, another quasar subclass, another dusty starburst. The little red dots do not settle easily into those inherited boxes. They appear at the edge of the known census and ask whether a missing phase of cosmic evolution has been hiding in plain sight. Perhaps they are galaxies undergoing compact bursts of star formation so intense that they briefly mimic something more exotic. Perhaps they are black holes wrapped in dense gas, luminous through accretion yet not yet embedded in the larger galactic forms familiar from later eras. Perhaps they are transitional objects, halfway between early galaxy and feeding nucleus, revealing a stage that older surveys blur away. In every version, they reinforce the same impression. The early universe is not sparse and simple. It is crowded with compact luminous systems whose nature is difficult to disentangle because structure, chemistry, and feeding black holes may all be maturing together. This impression becomes still stranger when it's placed beside another kind of relic, one that does not come from the early universe in the sense of ancient images, but from the passage of an interstellar object through the solar system. The sample script imagines an especially ancient comet, older than the Sun and carrying chemical traces from a vanished stellar environment. The known scientific landscape around interstellar visitors is more careful and less theatrical, yet it still opens a meaningful line of thought. The confirmed interstellar objects observed crossing the solar system are rare, fast, and chemically interesting because they are fragments of other systems. They do not belong to the Sun. They arrive from the wider galaxy, carrying material histories shaped under stars that may be older, younger, richer, or poorer in heavy elements than the one around which Earth forms. Even without assigning any single visitor a wildly precise age, the principle remains remarkable. Pieces of extinct or distant systems can drift through interstellar space for immense spans of time, preserving matter from environments the solar system never knew. That possibility changes the emotional scale of cosmic archaeology. A deep field image shows the universe as it was. An interstellar object can bring ancient chemistry into the present, not as light from long ago, but as matter surviving across galactic distances. It is a different kind of witness. Light tells what an object looked like in a vanished era. A comet or asteroid from another system carries direct material inheritance from that era into a new one, if interstellar fragments are common. Then the galaxy is not only a network of stars and planets, it is also a slow circulation of debris, a migration of relics carrying frozen records of older chemical settings. Some may be older than the solar system. Some may have formed around stars that are long dead. Some may preserve carbon-rich or water-poor signatures unlike the default patterns assumed from local comets. Each visitor would then be a small intrusion from a different chapter of galactic history. This matters because Webb's other discoveries are already implying that chemical complexity appears early and in varied forms. An interstellar relic from an older environment, whether directly observed or inferred through the broader study of such bodies, fits into the same widening picture. Matter does not stay neatly confined to the system that makes it. It travels. It survives. It carries memory. The galaxy becomes less like a set of isolated households and more like an immense archive in motion, with fragments from old stars passing into the neighborhoods of younger ones. The solar system is not sealed. It is exposed, at least occasionally, to visitors whose chemistry is inherited from alien origins. When all of this is gathered together, Webb begins to reveal a universe that reaches complexity earlier and more unevenly than the standard story once preferred. The first galaxies are not merely growing too fast, they're also processing their matter too quickly. The first luminous compact systems are not merely bright. They are chemically and structurally ambiguous in ways that suggest missing stages of development, interstellar fragments, real or strongly expected, imply that ancient environments do not simply vanish. They shed material into the galaxy's larger circulation. The cosmos is not waiting politely for simplicity to yield, step by step, to richness. It is producing richness in pockets, in bursts, through channels that overlap and sometimes outrun the supposed order of events. There is a broader philosophical temptation here, but the narrative does not need to indulge it fully. It is enough to notice that Webb repeatedly weakens the old comfort of gradualism. Not because gradual processes are false, many still operate. Stars still evolve through known stages, galaxies still merge, dust still condenses and drifts. But over and over, the telescope finds evidence that the universe also permits leaps, enrichment leaps, structural leaps, compact luminous phases that appear between the cleaner categories. The result is not chaos in the sense of disorder without pattern. It is a cosmos with shortcuts built into it, a cosmos able to become more elaborate before human models are ready for it to do so. One of the most powerful consequences of this earlier complexity is its effect on the imagination of later worlds. Dry rocky planets, carbon-rich atmospheres, dusty galaxies, giant black holes, all depend on chemistry that someone must forge first. If Webb is right that heavy element production and redistribution proceed with unusual speed in some early systems, then the inventory of possible worlds expands much sooner. Planet formation is no longer something reserved for an already mature universe. The materials for rocky surfaces and mineral atmospheres may begin spreading while cosmic history is still in its first act. That does not mean fully formed habitable worlds emerge instantly. It means the raw ingredients of diversity enter the stage early enough to change the range of what later eras inherit. The little red dots remain central here because they occupy the boundary between explanation and uncertainty. They are a visible sign that the early universe resists being summarized cleanly. Some may eventually turn out to be more ordinary than first feared. Some may be reclassified as active black holes in compact hosts. Some may become examples of brief but violent galactic phases. Yet even this process of clarification is revealing. The universe has discovered ways to hide its real nature behind compact brightness, dust, distance, and ambiguity. Webb is not simply cataloguing ancient objects. It is learning how easily the early cosmos disguises its own mechanisms. A tiny red point may be a galaxy, a black hole, a starburst, or some combination in rapid transition. The categories blur because the young universe itself may blur them. That blurring leads naturally to a new scale of concern. Once chemistry appears early and compact systems proliferate, a question arises about the larger arrangement of the cosmos. Are these anomalies isolated objects, or are they signs that structure on the grandest scales is also carrying hidden organization too soon? If galaxies can grow early, if black holes can feed early, if heavy elements can emerge early, perhaps even the patterns linking galaxies across the void are more ordered than expected. Webb begins to offer hints of that possibility as well. Some surveys suggest coordinated behaviors across enormous distances, as though widely separated systems share directional tendencies that ordinary local formation cannot easily explain. At the same time, studies of the cosmic web and large-scale magnetic structure hint that the space between galaxies is less empty and less passive than older pictures suggest. The same telescope that finds ancient chemistry in young galaxies and ambiguity in little red dots now begins to look at the architecture connecting those galaxies. And there too, in the largest structures of all, it starts to find signs that the universe may be carrying memory, orientation, and hidden order across distances too vast for ordinary coincidence to feel comfortable. By the time James Webb reaches this point in the story, the universe already looks less orderly than it once does. Expansion refuses to settle into one clean value. Galaxies appear too massive too early. Black holes race ahead of their expected histories. Chemistry matures before the timeline is supposed to allow it. Yet all of those anomalies still belong, in some sense, to local places. A galaxy is a place, a disk is a place, a black hole, even a vast one, remains a compact event inside a larger setting. The next disturbance is more unnerving because it shifts from objects to pattern. It asks not what one strange thing is doing, but whether very distant things are doing similar things together. It asks whether the large-scale universe, separated by gulfs so wide that no ordinary local influence can coordinate them, may still carry some hidden orientation, some buried memory, some preference written into the cosmic field itself. If that possibility is taken seriously even for a moment, then the mystery changes scale. It is no longer about exceptions scattered through a broadly neutral cosmos. It is about the possibility that the cosmos itself is not as neutral as it seems. This suspicion begins with a question as simple as rotation. Galaxies spin. That is not strange. Disks of stars and gas settle into rotation as angular momentum is conserved during collapse and merger. Some turn one apparent way on the sky, some the other. In a universe without large-scale preferred direction, the distribution of those apparent rotations should even out statistically when a large enough sample is observed. There will be local variation, small biases introduced by environment, and observational complications, but on sufficiently broad scales, no deeper symmetry is expected. The universe, in its largest geometry, is supposed to have no favoured-handedness. It should not care whether a distant spiral galaxy appears to turn clockwise or counterclockwise from a human viewpoint. And yet, in some analyses of deep survey data, a troubling pattern begins to appear. Samples of galaxies observed at great distance do not always distribute themselves with the serene indifference the standard cosmological picture would prefer. Instead, there seem to be directional imbalances, regions where one apparent sense of rotation appears more common than the other. This is not an easy claim, and astronomers treat it carefully because such results are notoriously sensitive to selection effects, image orientation, classification bias, and the mechanics of analysis. A preferred direction in galaxy rotation would be an extraordinary finding. It requires repeated checking and invites skepticism. But Webb makes the question harder to dismiss because it sees so deeply into the young universe and does so with enough resolution to let subtle structural patterns be tested in new ways. In some datasets, galaxies separated by vast cosmic distances seem to participate in a statistical asymmetry, too coherent to explain comfortably as a local environmental accident. The individual cases do not speak loudly. The pattern speaks only when many galaxies are gathered and compared. Yet once seen, even tentatively, it creates a peculiar kind of unease. Rotation is a memory of origin. If galaxies widely separated in space appear to favour related orientations, then the universe may have inherited some large-scale angular imprint that later structures still carry. There are restrained ways to interpret this and more radical ones. The restrained view says the signal may be a byproduct of hidden biases in the data or in the methods used to classify spiral-handedness. That remains possible and must remain on the table. Deep sky surveys are difficult. A faint distant galaxy can be distorted by distance, dust, lensing, and noise. A sample can be shaped by what the telescope is most likely to detect. Any claim of cosmic handedness must pass through that minefield. Yet the more radical possibility does not disappear simply because caution is warranted. If the asymmetry is real, then the universe may not be globally isotropic in the neatest sense. It may preserve a preferred direction, a leftover twist from conditions near the beginning, a rotational bias impressed on large-scale structure before galaxies fully form. That thought is unsettling because it reaches back toward origin itself. A rotating universe is not merely a universe with spinning contents. It is a universe whose geometry and evolution may carry the trace of a large-scale angular momentum. Under such conditions, some regions of space could evolve with subtle directional differences. Expansion might not be perfectly uniform in every direction. Matter might clump with slight asymmetries. Even the interpretation of cosmic background signals could shift if the underlying framework has a built-in axis or shear. The old confidence that on the larger scales the universe looks the same in all directions would become less secure. What was once treated as a foundational simplification would become an approximation, perhaps useful, perhaps profound, but incomplete. This possibility begins to resonate with the older tension in cosmic expansion. If the universe already resists one consistent account of how fast it expands, then hints of large-scale directional preference become harder to dismiss as philosophically irrelevant. A preferred axis, a residual rotation, or some anisotropic feature in the underlying geometry could in principle affect how different measurements sample the cosmos. That does not solve the tension on its own. It does something stranger. It suggests that the expansion discrepancy and the spin discrepancy may not be isolated embarrassments. They may be separate surface expressions of a deeper asymmetry in the universe itself. A cosmos born with even a slight rotational tendency would no longer be the perfectly impartial stage described in its simplest form. It would be a structure with memory. James Webb adds a second layer to this large-scale unease by helping reveal that the space between galaxies may be more organized than it appears. For many years, the cosmic web serves as a useful image for the distribution of matter on the larger scales. Galaxies are not spread uniformly. They gather in filaments, clusters, walls, and nodes, separated by enormous voids. Dark matter shapes this structure gravitationally, pulling ordinary gas into a vast network. The web metaphor is powerful, but often it remains visually abstract, a map of density more than a living physical medium. Webb's observations, alongside other instruments and models, begin to suggest something richer. The filaments linking galaxies are not only channels of matter, they may also carry magnetic structure, energetic history, and internal organization more intricate than the older picture allows. Magnetic fields in astronomy are elusive because they rarely announce themselves directly. They reveal their presence through polarized light, synchrotron emission, particle behavior, and the shaping of plasma. In galaxies, they are already important, influencing gas motion, star formation, and cosmic ray transport. On the scale of clusters and intergalactic filaments, their role is harder to trace. Yet hints of ancient magnetism stretch through the large-scale universe, and some analyses suggest patterns whose complexity is almost unsettling in its elegance. Instead of simple uniform threads, the magnetic structure associated with large-scale matter distribution may contain nodes, branches, and reconnecting networks reminiscent, in a purely visual and mathematical sense, of neural organization. The analogy must not be forced. The universe is not a brain, and such language can mislead if taken literally, but the resemblance in pattern is enough to provoke thought. On the grandest scales, matter and field may arrange themselves into connected topologies more intricate than a passive scaffold should require. What makes this especially strange is the timing. If significant magnetic organization exists very early in cosmic history, then it is not merely a late byproduct of mature galaxies polluting their surroundings. It may be part of the way large-scale structure itself evolves from the start. Magnetic fields can shape gas collapse, alter shock behavior, guide charged particles, and influence how matter flows along filaments. Their presence does not replace gravity, but it complicates the clean gravitational story. A galaxy forming inside a magnetized filament is not forming in a neutral void. It is emerging inside a medium with memory, tension, and direction. That begins to sound familiar. Once again, the universe looks less like a blank stage and more like an environment already carrying inherited patterns before the visible actors fully appear. There is also a subtler consequence. Fields and rotation are both forms of order that survive across time. A galaxy may forget many details of its earliest gas clouds, but it remembers angular momentum. A filament may evolve, but magnetic structure can preserve and redistribute energy in ways that shape later collapse. If Webb is really exposing traces of large-scale preferred orientation and ancient field complexity, then the cosmos may be more historical than it seems. Not in the trivial sense that everything has a past, but in the stronger sense that primordial asymmetries can survive into later eras and still be read in the behavior of systems separated by unimaginable distances. The universe then begins to resemble an object with deep internal persistence. Early conditions are not washed away as completely as the simplest models prefer. This is where speculation begins to widen beyond standard cosmology, without quite leaving the ground of observation. One possibility is that the large-scale asymmetries are real, but natural consequences of conditions already allowed by modified versions of early universe physics. Perhaps inflation, the rapid expansion thought to smooth the young cosmos, is not perfectly featureless. Perhaps relic fields survive from earlier phases. Perhaps matter and space-time carry subtle anisotropies that become visible only when extremely large samples of distant galaxies are studied. These ideas remain within the broader scientific landscape, even if they are not confirmed. Another possibility is more radical and therefore more difficult to handle with restraint. If the observable universe carries a preferred direction and inherited rotation, then it may not be a closed self-sufficient system in the way standard cosmology describes. It may be embedded within a larger geometric context that imposes asymmetry from outside the ordinary horizon of observation. This is where theories such as black hole cosmology begin to reappear, not because the data require them, but because certain anomalies make them harder to dismiss entirely as a imaginative excess. If a universe forms inside a rotating parent structure, then large-scale handedness in galaxy rotation acquires a possible origin. The cosmos would inherit angular momentum rather than generate it from nothing. Likewise, if space-time on the larger scales carries memory of a deeper embedding, then the apparent mismatch between different expansion measurements could reflect not only missing local physics, but a broader geometrical misunderstanding. Such ideas remain speculative. The known facts come first. Galaxies may show puzzling rotational asymmetries. The cosmic web may carry more organized magnetic and structural complexity than once assumed. Those are the anchors. The interpretive widening comes afterward, and only carefully. Still, even careful widening changes the atmosphere of the story. It suggests that the stage on which cosmic events unfold may itself have a directional grain. The emotional force of this section comes from the simple thought that very distant things may not be independent in the way they ought to be. In ordinary cosmological intuition, two galaxies separated by millions or billions of light years are causally disconnected in every local practical sense. They form from their own environments, influenced by nearby matter, not by some grand unseen coordination. If patterns across such distances begin to align, even weakly, then local explanation starts to thin out. The universe becomes less like a random spread of islands and more like a fabric whose threads carry shared tension. Webb, by pushing observation deeper and more precisely into the ancient sky, increases the sensitivity of that test. It does not prove a rotating universe. It does not prove that magnetic filaments guide cosmic history like invisible roads. What it does is make the old assumption of absolute large-scale neutrality feel less secure. By now, the recurring pattern of Webb's discoveries reaches a new intensity. First, it reveals objects that are too old for their age. Then it reveals processes that are too violent for the old timeline. Then it reveals worlds that remain active in the wrong conditions. Then it reveals chemistry that matures too soon. Now it begins to hint that the very layout of the cosmos may carry preferences and inherited structures across scales too large for comfort. Each step preserves the same rhythm. A measured fact appears. That fact strains an expectation. The strain opens a mystery. The mystery invites a broader view of what the universe may be. The scale changes, but the logic remains. And with the scale now stretched to the architecture of the cosmos itself, another question begins to form in the dark. If galaxies across vast reaches can show coordinated tendencies, and if the web connecting them is charged with more structure and memory than once believed, then what happens where gravity becomes most extreme? What happens near the places where space-time is forced into its deepest curves, where light bends, time delays, and matter crosses the edge of no return? The next step in the story does not leave large-scale structure behind. It takes the same suspicion of hidden order and carries it into regions where the geometry of the universe itself may begin to fray. The earlier anomalies can still be imagined as failures of timing, chemistry, or formation. Galaxies may grow faster than expected. Black holes may feed more violently than models allow. Rogue planets and scorched atmospheres may broaden the catalogue of what matter can do. But there is another threshold beyond which the tone of the story changes. It is the threshold where the strange behaviour no longer belongs only to the objects inside the universe, but to the geometry through which those objects are seen. At that point, the question is no longer only what forms too early or survives too long. The question becomes whether space-time itself, the framework that holds distance, motion, and causality together, behaves with less smoothness and less serenity than modern physics usually assumes. James Webb does not announce such a conclusion directly. No telescope could. What it does is expose enough pressure points, enough regions of extreme distortion, enough persistent irregularities, that the old picture of a calm geometric stage begins to feel increasingly provisional. A natural place for that unease to begin is gravitational lensing. Einstein's general relativity predicts that mass curves space-time, and light follows those curves. When a massive galaxy or cluster lies between Earth and a more distant source, the foreground gravity can bend the light of the background object into arcs, multiple images, magnifications, and time delays. This is not a speculative fringe effect. It is one of the most reliable large-scale confirmations of relativistic gravity. Astronomers use it as a tool. Lensing lets them weigh galaxies, map dark matter, and study sources that would otherwise be too faint to see. In its ordinary form, gravitational lensing is a triumph of order. The same curved geometry that seems abstract in theory becomes visible on the sky as a predictable distortion. Yet as Webb pushes lensing studies deeper and with more detail, some systems begin to look less like straightforward demonstrations of elegant theory and more like regimes where the theory is being stretched to its practical limits. Consider the cases where a foreground galaxy bends the light of a distant background object into several distinct images, each one arriving along a slightly different path through warped space-time, because those paths are unequal in length and pass through different gravitational potentials. The light does not reach Earth all at once. One image may show the source at one moment, another the same source at an earlier or later moment. A single distant galaxy can therefore appear several times in the sky, its history split into separate beams by the gravity of something in front of it. This is already strange in a calm, precise way. Time becomes visible as geometry, because remains intact, but sequence is displaced into space. The same object is seen at different ages simultaneously. Webb excels in these systems because its sensitivity and resolution in the infrared let it study faint background sources and the structure of the lensing mass with uncommon precision. In some lensing configurations, it is not simply revealing a curiosity. It is turning distorted space into a natural experiment on the behavior of gravity. What makes the atmosphere darker is not that lensing happens. It is that the inferred mass distributions required to explain some strong lensing systems are not always as smooth or as simple as older models prefer. Dark matter, which should form broad halos around galaxies and clusters, seems to show clumpiness, substructure, and a symmetry at scales that matter for how the light is bent. Some of this is expected. Real halos are not perfect spheres. They contain history. They contain smaller bound structures, merger relics, and internal complexity. But as the quality of observation improves, the geometry required to reconstruct certain lenses begins to reveal a universe in which the hidden scaffolding is more intricate than the cleanest theoretical templates suggest. The lens does not merely magnify, it exposes roughness in the unseen mass. A background galaxy stretched into arcs and repeated images becomes a map, not just of one object, but of the invisible irregularity of the space in front of it. That by itself does not imply a failure of relativity. It often implies only that dark matter is difficult to model in exact detail. Yet there is a psychological shift in what these lenses show. The old dream of using them as almost transparent geometric instruments gives way to a recognition that the medium of distortion is itself knotted and uneven. The warped light carries not one clean message, but a layered one. It tells the history of the source, the structure of the lens, the presence of dark subhalos, the timing of cosmic expansion, and the small irregularities of geometry all at once. Webb makes that layered reading richer and more difficult. The universe does not bend light through smooth glass. It bends it through crowded gravitational weather. This feeling deepens near black holes, where curvature is no longer mild. At the centre of the Milky Way lies Sagittarius, a star, a black hole of roughly 4 million solar masses. Compared with the monstrous engines in some distant active galaxies, it is modest. Compared with anything familiar to ordinary experience, it is an abyss. For decades it remains half-hidden, its surroundings obscured by dust and its behaviour revealed only indirectly through radio, infrared, and X-ray work. Webb's contribution is not to discover the black hole, but to watch it with a steadiness and sensitivity that add a new kind of intimacy. Over repeated observations, Sagittarius, a star does not behave like a calm static sink. It flickers, it flares. Its brightness changes in irregular patterns that seem to emerge from turbulence, magnetic reconnection, and the restless motion of plasma orbiting near the edge of no return. There's nothing unscientific about this variability. Accretion flows around black holes are expected to be messy. Gas spiraling inward is heated, magnetized, shocked, and stretched by enormous tidal forces. Yet the closer those emissions come from regions near the event horizon, the more they arise from conditions where ordinary intuition about space and time loses traction. Matter orbits at a significant fraction of light speed. Paths of light are bent back on themselves. Time passes differently relative to distant observers. Magnetic fields twist and reconnect in plasma so hot and sparse that the language of fluid motion, particle motion, and radiation all begin to blur. When Webb records irregular bursts and sustained flickering from this region, it is observing not merely a black hole feeding. It is observing a regime in which the known laws are still trusted, yet they are operating under maximal strain. The key unease lies in the boundary between trust and strain. General relativity works astonishingly well. Quantum theory works astonishingly well. But black holes are where their coexistence becomes philosophically unstable. An event horizon is described classically as a smooth surface in space-time, not a material shell. Yet the physics of information, entropy, and quantum fields around that surface remains unresolved in deep theory. Webb does not measure quantum gravity. It does something more suggestive. It watches real matter and light behave in a region where the unresolved tension between classical geometry and quantum law is not abstract. Every flare from the inner accretion flow comes from a place where the known map of physics is still navigable, but perhaps incomplete. Each sudden brightening hints at magnetic violence or in falling clumps of matter, but also reminds astronomers that this entire environment exists at the frontier where space, time, and information are hardest to reconcile. The same frontier appears in a different form when galaxies or clusters create extreme time delays through lensing. A foreground mass can show a background source at several different stages at once, because space-time geometry literally separates its history into multiple arrival paths. This is not only a visual trick, it is a direct manifestation of time being dragged and folded by gravity. In ordinary life, cause and sequence seem absolute. In these systems, sequence depends on root. The universe itself turns into a machine that delays and duplicates moments. Webb reveals this with a precision that strips away any temptation to treat it as mere textbook elegance. A lensed galaxy is not simply distorted, it is disassembled into temporal fragments. The sky can contain one object several times over, each image carrying a different age. Under enough gravity, even chronology stops arriving in one piece. That fact opens a narrow door to deeper speculation. If mass distributions are more irregular than expected, if dark matter substructure alters the exact geometry of lensing, if different pathways through curved space-time split light into subtly different versions of the same source, then the large-scale universe is full of places where reality is already more fractured in appearance than ordinary intuition admits. This is not yet space-time breaking down. It is space-time revealing how alien its normal operation becomes under pressure. But once that has been seen enough times, the mind begins to ask whether the smooth manifold described by relativity is always the full story, or whether at certain scales and under certain stresses the underlying structure may be less continuous than it seems. The sample script pushes this toward ideas such as quantum foam, cosmic strings, and vacuum instability. Those possibilities belong to the outer boundary of theoretical speculation, and the known evidence is not decisive enough to treat them as observational facts. Yet they are not arbitrary inventions. They arise because mainstream physics already predicts that the smoothness of spacetime should be an emergent approximation, not the final truth. At very small scales. Quantum field theory and gravitational thought experiments both suggest that the classical fabric may have a deeper granular or fluctuating character. Normally such scales are hopelessly remote from astronomical observation, but black holes, the early universe, and extreme gravitational lenses are among the few arenas where tiny structural effects might, at least in principle, leave larger shadows. When Webb observes persistent anomalies near extreme systems, science must first exhaust ordinary explanations. Yet the ordinary explanations themselves now exist in a context where the possibility of deeper geometry cannot be wholly ignored. Dark matter adds another layer to this pressure. It is already a strange presence, invisible except through gravity, shaping galaxies and clusters while revealing none of its inner nature directly. Webb's deep imaging of clusters and tidal debris hints that dark matter is not merely passive background architecture, where galaxies are stretched, stripped, and rearranged across large distances. the unseen mass controlling those events begins to feel active in a hidden way, not active through light or heat, but active through the severity of the geometry it creates. Stellar streams arc through space as if pulled by forces belonging to a map no eye can see. Galaxies are bent, shredded, or suspended inside wells defined mostly by invisible matter. Light from more distant sources then passes through those same wells and emerges split, delayed, and magnified. The universe begins to look like a place where visible structure is only the luminous skin of a much deeper geometric machinery. This matters because geometry is the one thing earlier cosmology often treats as stable. Matter changes. Stars live and die. Galaxies merge. But space-time itself, outside rare extreme environments, is assumed to behave smoothly. Webb does not overthrow that assumption. It makes it harder to take for granted. The more clearly the telescope reveals violent curvature, hidden substructure, and temporal fragmentation through lensing, the more the classical image of smoothness begins to feel like a low-pressure approximation. Reality under ordinary conditions may indeed appear calm, but under enough mass, enough density, enough compression of history into one line of sight, calm geometry turns into something almost alive with distortion. There is a final thread linking this section to everything that comes before it. Each earlier anomaly suggests that the universe is more efficient, more permissive, or more organized than the cleanest models predict. Here that same pattern reappears at the level of the stage itself. Light is not only delayed, it is multiplied. Time is not only measured, it is routed. Invisible matter is not only inferred, it is seen through the violence it imposes on space, near black holes. Emission is not only bright, it is produced in a zone where the deepest theories of nature stop fitting together comfortably. The universe no longer looks like a passive background with interesting objects inside it. It begins to look like a dynamic geometry that sometimes exposes its own internal tension. And this is why the final step in the narrative cannot remain at the level of local anomalies, however dramatic they are. If expansion is inconsistent, if early structures are too mature, if the cosmic web hints at large-scale direction, and if space-time under extreme gravity begins to reveal a rougher and more unstable character than expected, then the remaining possibility is the widest one of all. Perhaps the trouble does not lie in one process, one class of object, or one missing correction. Perhaps the observable universe sits inside a larger structure that current cosmology only describes from within, never from above. In that case, Webb's strangest findings would not be separate surprises. They would be glimpses of the container itself, indirect signs that the cosmos may not be a complete self-contained whole, but a region shaped by a deeper geometry whose edges can only be felt through contradictions. By the time the story reaches its final edge, no single anomaly is carrying the full weight anymore. The disturbance now comes from accumulation. A mismatch in cosmic expansion might once have been treated as a technical tension. Oversized early galaxies might have been filed as an embarrassment for simulations. Premature black holes might have suggested only that feeding and collapse happen faster than expected. Strange rogue worlds and chemically distorted disks might have widened planetary theory without touching cosmology itself. Coordinated patterns in galaxy rotation might have remained disputed statistics. Violent lensing and restless black hole light might have belonged to the ordinary strangeness of extreme gravity. Yet James Webb has a way of making separate puzzles lean toward one another. The more it looks, the more these problems stop behaving like isolated cracks and begin to resemble pressure marks from a larger shape pressing through the known universe from behind. At that point, the most unsettling possibility no longer concerns one object or one process. It concerns the container. It asks whether the observable universe, the whole expanding field of galaxies, radiation, and space-time that human cosmology tries to model from within may itself be a structure nested inside something larger and stranger. This is not a standard conclusion. It is not the accepted framework of modern astronomy. But it exists at the edge of serious thought because some of Webb's findings make the ordinary framework feel less self-sufficient than it once does. If the universe carries a preferred direction, if its expansion is not fully captured by one coherent account, if black holes appear too early and too often, and if the largest structures seem to preserve hidden orientation or memory, then the possibility emerges that what is being observed are not merely flaws in details of the model, but hints that the model is describing a region without seeing the whole architecture to which that region belongs. One speculative idea takes this possibility farther than most astronomers are willing to go, yet it persists because of how elegantly it gathers disparate tensions into one image. The idea is black hole cosmology. In its broadest form, it imagines that what is experienced as the birth and expansion of the observable universe may correspond, in a larger surrounding reality, to the interior of a black hole. This does not mean the universe is a black hole in the simple everyday sense. It means that the horizon structure, the trapped geometry, and the inherited rotational and gravitational properties of a black hole in some parent cosmos might generate a region like the one human beings observe from within. The Big Bang, under such a view, is no longer the absolute beginning of everything. It is the beginning of the interior history of one bounded cosmic domain. The attraction of the idea is not only its drama, it is the way it gives a possible parent explanation to several otherwise unrelated anomalies. If the observable universe forms inside a rotating parent black hole, then large-scale directional patterns in galaxy spin become less mysterious. They are not spontaneous symmetry violations in an otherwise directionless cosmos. They are inherited angular momentum, an imprint carried inward from a larger geometric structure. If the expansion of the universe appears inconsistent when measured in different ways, then perhaps the inconsistency reflects not merely missing local physics, but the difficulty of interpreting an interior space-time whose global curvature is misunderstood from the inside. Dark energy, in this view, may not be a new fluid or a changing vacuum property at all. It may be the observational signature of living inside a geometry whose deeper context remains hidden beyond a horizon. This remains speculative, and the story must say so clearly. Webb does not prove that the universe lives inside a black hole. It does something subtler and more dangerous. It makes the conventional alternative feel less secure. That is a very different thing. In science, a radical idea does not become persuasive merely because it is imaginative. It becomes hard to dismiss when more conservative explanations must absorb too many contradictions at once. The standard cosmological model is still extraordinarily successful. It predicts the broad behavior of the cosmic background, the growth of large-scale structure, and the composition of the universe with remarkable power. Yet Webb keeps revealing places where that success seems thinner near the edges. Early cosmic structures look too mature. Black holes look too precocious. Expansion looks too conflicted. The universe begins to resemble a theory that works extremely well within a domain of approximation, while something about the larger reality outside that domain remains unseen. The black hole cosmology picture is only one attempt to name that unseen reality. Other possibilities remain entirely within more conventional physics. Perhaps dark energy changes with time. Perhaps extra particles or hidden fields shape the early universe. Perhaps dark matter has richer interactions than gravity alone. Perhaps inflation leaves subtle anisotropies that survive into galaxy rotations. Perhaps the Hubble tension will eventually narrow through improved calibration, while the early galaxy crisis softens under better mass estimates. All of these remain possible. The known facts do not force the most radical interpretation. Yet the radical interpretation remains interesting because it turns the emotional logic of Webb's discoveries inside out. Instead of asking why the observable universe contains so many premature structures and lingering asymmetries, it asks whether such features are what any embedded interior cosmos would naturally display if it inherits conditions from a larger parent geometry. There is another reason the idea persists. Black holes themselves no longer look like simple endpoints. Throughout Webb's observations, they keep behaving like generative objects rather than final graves. They appear early, they influence galaxy formation, they may form by direct collapse, by extreme feeding, perhaps even by primordial roots. They do not sit passively at the ends of stellar histories. They organize matter, light, and time around themselves. Once black holes begin to look less like dead ends and more like engines of structure, it becomes easier, at least conceptually, to imagine that the universe on the larger scale might emerge from black hole-like geometry as well. The same type of object that devours matter in one context might seed an entire interior spacetime in another. That is not an observational fact. It is a conceptual resonance. But it is precisely the sort of resonance that becomes harder to ignore when a telescope repeatedly discovers that black holes are more central to cosmic history than older narratives suggest. The horizon becomes the key image here. In ordinary black hole physics, the event horizon marks a boundary beyond which return is impossible. From outside, it is a limit of information and escape. From inside, if any inside perspective can be meaningfully imagined, it is simply the surrounding structure of reality. Human cosmology already lives with one great horizon, the observable limit beyond which light has not had time to reach Earth since cosmic history begins. That horizon is not an event horizon in the same strict sense, yet the similarity is psychologically potent. Every cosmic model is built from within a bounded region of light. The possibility that this bounded region is not everything, but the interior manifestation of a larger and unobservable structure, introduces a profound shift in scale without requiring an immediate violation of known local physics. From within such a universe, local laws may still look smooth and self-consistent most of the time. Only at the extremes, in early structure formation, large-scale anisotropy, and the behavior of deep gravity, might clues begin to appear that the local map is not the whole territory. This is why Webb's discoveries feel cumulative rather than merely exotic. Each one by itself can be discussed inside ordinary astrophysics. Together they begin to change the emotional shape of the cosmos. The universe ceases to feel like an open plain expanding from a single comprehensible beginning. It starts to feel like an interior environment whose rules are still locally meaningful but globally incomplete. The observable cosmos may be only a layer, a cross-section, or a trapped region of a larger reality whose geometry cannot be seen directly. In such a picture, the most distant galaxies are not merely far away. They are features on the inner wall of a domain whose full structure remains concealed by the very space-time that makes observation possible. And yet the narrative cannot harden into certainty here, because the point of Webb's lesson is not that one new cosmology has replaced another. The point is that the universe has become less willing to be summarized. The deeper the telescope looks, the less the old habit of closure survives. It is still possible that better simulations, larger datasets, improved spectroscopy, and more patient statistical work will gradually absorb many of the current tensions. Some little red dots may become less mysterious. Some early galaxies may prove smaller or more black hole dominated than first thought. Some directional patterns may dissolve under stricter analysis. Some expansion discrepancies may narrow, though they have resisted that hope so far. Science often advances by passing through moments when contradictions feel revolutionary and later become understandable. That possibility remains real and important, But even if much of the current unease eventually settles, Webb has already altered something fundamental. It has shown how quickly confidence in a completed cosmic story can fail when the universe is examined with enough depth. The final mystery, then, is not whether one particular speculative model is true. It is whether reality on the larger scales is intrinsically more layered than any single observational era can comfortably grasp. Perhaps humanity lives in a universe that is locally legible but globally concealed. Perhaps the observable cosmos is one chamber in a hierarchy of chambers, each with its own horizons, each appearing complete to those inside until instruments become sensitive enough to notice inherited asymmetries and unexplained tensions. Perhaps black holes are not merely endings, but transitions. Perhaps cosmic expansion is not the whole motion, but only the interior appearance of a larger fall through hidden curvature. Or perhaps something simpler but equally profound is true, and Webb is only beginning to reveal it. What remains after all the oversized galaxies, the premature black holes, the orphan worlds, the wrong chemistries, the synchronized spins, and the strained geometry is not an answer, but a new posture toward the sky. The universe no longer appears merely vast, it appears internally restless, as though its visible order sits over deeper, unresolved dynamics. Webb does not destroy cosmology. It makes cosmology unfinished again. It restores danger to the idea of explanation. A measured contradiction may be the surface trace of a buried structure. An early galaxy may be a sign of hidden efficiency. A black hole may be an inheritance from a stage of reality not yet understood. A pattern in the larger structures may be the faint memory of a direction human beings are not supposed to see, and so the narrative reaches its outer limit without truly arriving. The telescope has not found a final revelation waiting intact in the dark. It has found a universe that keeps resisting finality. Every time the field of view widens, something that should have remained local begins to look global. Every time a mystery appears to belong to one class of objects, it echoes somewhere else in another form. The cosmos revealed by James Webb is not only stranger than expected, it is more connected in its strangeness. That may mean there is a hidden law tying the anomalies together. It may mean there is only a hidden layer of complexity that the current generation of theory has not yet learned how to describe. Either way, the old image of a finished cosmic story is gone. In its place remains a darker and more open possibility. The universe may not simply contain mysteries, it may itself be one.